All right. Well, welcome everyone to session number 6 of the SmallSat conference. This is Advanced Technologies 1, and we've got a few of these sessions, but this one has definitely got quite a few great papers and presentations. I hope everyone has had a chance to look at the content that's been posted online. All the different recordings of webinar recordings from yesterday are coming online, but clearly all the papers, Swifties, and other talks are all available, so I hope you're enjoying those. We have quite a few registrants participating, and we're seeing good traffic, so I encourage folks to keep engaging in the content. For today's session, I'd like to first now introduce our moderator, who will be guiding us through sort of a panel discussion with the presentations in this session, leading them through some opening remarks and a Q&A, and then into open audience questions to follow as time permits. And so we're looking forward to a rich exchange. One request of the audience is please use the Q&A tab to submit any questions you may have, not the chat tab, but the Q&A tab. And we'll be making sure that those get back to our panelists to address as we go forward. So without further ado, let me introduce our moderator, Mr. Darren Rowan from the Aerospace Corporation. Darren is a department director for the Small Satellite Department at the Aerospace Corporation. He got involved with small satellite development starting in 2011, where he was the lead developer for one of the first CubeSat-sized attitude determination and control systems. And prior to joining the small satellite revolution, he worked in Northrop Grumman's space technology supporting control systems analysis for Class A spacecraft, so kind of two extremes in some respects. Completed his combined master's bachelor's program in EE at Rochester Institute of Technology, focusing on control systems. Darren, over to you.
Well, thank you, Aaron. Welcome, everybody. Thanks for joining for this question and answer session for Advanced Technologies, the first session for this group. And I'm going to introduce our first paper, which is a foldable, compact, and lightweight solar array substrate with large deployable wingspan for small spacecraft. And we have Calvin Lee from the Johns Hopkins University Applied Physics Laboratory. He's going to give an overview, and then we'll start with some questions.
Hi, good afternoon. My name is Calvin Key from Applied Physics Lab, and I'd like to just summarize the paper. It's a very mechanical testing heavy paper, particularly in regards to the composite panels that we built for the solar array. It's very compact, and it's using a material that we haven't delved into before, and we did a lot of tests to validate the material distortions in thermal environments, and did deployment testing and correlated that with Adams analysis, and just trying to bring this this technology up to a TRL6 so that we can basically put it into a spacecraft that is in the Express class size. So Express class is the size between a 12U CubeSat and a ESPA class, which is 180 kg. So between 30 and 180 kg.
Okay.
So that's, go ahead.
Yeah, thank you very much for that overview. Let's start with a couple of questions we have here. So certainly the lighter weight solar panel material is clearly beneficial for small spacecraft. Do you have any, do you envision later applications where this same type of technology could be used for larger arrays on large spacecraft as well?
So for larger arrays on larger spacecraft, the benefit of this compact packaging is probably not so transferable. It depends on the weight to area ratio. So we need to develop that a bit more and do some analysis to determine the stiffness requirements and strength.
Okay. During your test campaign, I certainly saw on the paper you had quite a bit of environmental testing. Did you run into any surprises that motivate future iterations or improvements that you might consider in the future?
That there were no surprises. It was more of like a sort of a aha discovery, like that this material worked in those environments, and the compliance of the core material was pretty good in these environments. So it can be developed a bit more.
Okay, well, we are going to be moving on to the next speaker, and if we have additional time at the end and other questions come in, we may be able to revisit later in the session.
Thank you.
All right, so the next talk we have coming up is from Chris Wilson at the NASA Goddard Space Flight Center, talking about the SpaceCube Intelligent Multi-Purpose System for enabling remote sensing, communication, and navigation in mission architectures.
I'm sorry to jump in really quickly, Darren. Apologies for the interruption. We're looking for 3 authors related to the Aerospace Corporation Automated System Identification paper, the Elroy from Lanel, and the Deployable Optics for CubeSats. If you are one of the authors or presenters for those 3 papers, please identify yourself in the chat forum so we can bring you in and make you available for this session. Thank you. Thanks, Darren.
Thanks, Aaron. Okay, back to Chris Wilson. If you want to start with a 1-minute overview of the paper.
Great, thank you so much. Good afternoon, everyone. Thanks for joining us today in this virtual talk. It's
Chris,
my pleasure to.
Your video didn't come up yet. Just I want to double check that.
Yeah, I don't have video for this one.
Okay, so we'll just listen. Thanks.
And it's probably for everyone's benefit as well. Anyway, it's my pleasure to be able to produce SpaceCube. IMPS, our intelligent multi-purpose system for enabling remote sensing, communication, navigation, and mission architectures. So this is our reusable architecture for building these small CubeSat-sized payloads for onboard processing. In our paper, we cover the CS squared CubeSat card form factor, which kind of gives some specifications on how to build cards that would fit and work with our system. We also uncovered our latest CubeSat processor card, the SpaceCube V3 Mini, which features this massively configurable Xilinx Kintex KU060, which if you're an FPGA designer, it's pretty awesome because it allows you to do a lot of great work with Xilinx tools and new developments with the Xilinx DPU system. And then finally, we described our experience with creating intelligent systems by combining our SpaceCube Mini Z, which is an SoC-based system, working in tandem with our SpaceCube V3 Mini, which is the FPGA, the large FPGA system, to do hardware acceleration for a computer vision application called semantic segmentation.
Okay, very good. Thanks for the quick overview. A couple of questions we have here for you. So the first question is, CubeSat-sized vehicles are often very limited with respect to heat dissipation. One of the configurations you showed, the AI processing box, lists over 31 watts for system power. Getting the heat out of the electronics box is only part of the overall system solution. Is dissipating this amount of heat really sustainable for CubeSats? Any thoughts on how it would be addressed thermally?
Oh, that's a great question. Yeah, so one of the crazy parts with a lot of the AI processing especially is since you need so much processing capability, you really do bring up the power. So as part of the solution, you'll notice that we have wedge locks, and the reason we selected those was because you can build basically like a heat sink clamshell that goes over the board and connects to the CubeSat or small payload chassis to really dissipate some of the heat. So yeah, there are definite thermal challenges that we'd have to face, and sometimes that involves cycling your operational modes as well.
Okay. Have you considered more advanced thermal solutions for integration into this, such as phase change materials, for example?
So our group at the Science Data Processing branch is focused on mostly the computational aspects of delivering these payloads. We actually have a great mechanical team and thermal team with materials engineering support. And honestly, I don't know anything about it, so I really can't comment here.
Okay. We had another question about the connectors and the wedge locks. So with the rigid backplane, how do you avoid the wedge locks from mechanically loading the C-ray connectors and causing a reliability issue?
That's a great question as well. So unfortunately, I'd probably have to send a follow-up for that one, since our mechanical team has really been working on figuring out all of those types of questions for integrating it into the backplane. So I'm really not great on on the mechanical materials / thermal side. If you guys have managed to pick that up.
Understood. Another question we have is about the so deep submicron CMAS is known to have high TID ratings. Single vent upsets and latch up can be mitigated through the design, but in the end, reliability is also tied back to the processes used. How did you address these kind of reliability issues with the components?
If this is a general fault tolerance question, there's a lot that goes into the general SpaceCube approach for how we build cards, but it does rely on qualified parts and a lot of screening and testing in advance. For the actual FPGA portions, for single vent upsets on configuration memory and stuff like that. So part of my passion is actually studying fault tolerant techniques. So I mentioned there are a couple different boards. So depending on the architecture you select, there are going to be different fault tolerant modes that you can deploy to mitigate against SEE. So it really depends on which card. For the SpaceCube V3 Mini, we also have a radiation hardened monitor FPGA that's also on the board that we can use for like configuration scrubbing, reprogramming, stuff like that. And that's in addition to a lot of the techniques you'd normally deploy on an FPGA as well, like TMR and stuff like that.
Okay, can you tell us a little bit about the programs that intend to use this new architecture?
Oh, absolutely. So so the great thing about building and designing cards in this form factor is specifically that you can apply it to a lot of different domains. So as a computing group, the one we targeted immediately was intelligent systems. So there was a really cool proposal, if you guys haven't seen it, by DARPA called Blackjack, which talked a lot about doing some pretty interesting intelligent solutions. So one of the areas we really find working on these solutions is specifically for artificial intelligence, and you can apply a lot of those to like cognitive radio and stuff like that. In the card form factor, we also have several other cards that fit within the box, like a GPS and an SDR and stuff like that. So you can build the communication navigation portion, which we also talk about in the paper as well. But our group really focuses mostly on the computing aspect. But I mean, there are a lot of different places that high performance onboard processing is advantageous, especially for us. Like a compression is a huge topic as well, in addition to onboard data product generation. Okay.
Can you also talk a little bit about the power draw for the different processing boards?
So this is a trick question because for a lot of the different processing boards, right, we've got an FPGA on it. And if you're familiar with FPGA design, a lot of so there's like the static power for just turning the system on, but then the actual power draw is dependent on what application you have and how much of the FPGA you're utilizing. So each of those cards has different ratings. So I think some of those are in some of our other papers cited within that work.
Oh, that's good to know. We can redirect people there. All right. Well, thank you very much, Chris. I think we're gonna move on to the next paper. So I see we were able to locate David Palmer. So we're gonna switch to the progress towards the Elroy satellite license plate. And we have David Palmer from Los Alamos National Laboratory to David. So we'll start with a 1-minute overview, and then we can take questions.
Okay. So the idea behind Elroy is that you can put a little flashing light on your satellite, and this is just a mock-up, but this is the size of device that you need, and most of the size. This is a couple of square centimeters of solar panel, which is enough to produce about a milliwatt of laser light. And if you pulse that light in just the right way and look at it with a small telescope, around 35 centimeters is what we're using, with a photon counting detector, then you can actually pick up the signal and read off an identification number. And so you can put one of these on everything which goes into space. And if you want to know, hey, what's that dot of light? Then you just point your telescope at it, you find out, look it up in the registry, and it says, if in case of trouble, contact blah, blah, blah. And so if that satellite is on a collision course with your satellite, you can call them up and say, hey, can you avoid hitting us? And that's a good thing.
All right, thank you. Thank you for the overview. It was the NMTSat that attempted to do the first demo of the system. Is that right? What was the volume of the components in that demonstration?
Okay, in that demonstration, we used a single 1U PC104 card, and it was an inch thick, just because we used a large diffuser on the laser. This is laser light, and you can either do a lot of calculations to show, oh, a milliwatt of light isn't going to hurt anybody, or you can spread it out on a large diffuser and it obviously won't hurt anybody. And so in this case, having a large volume was cheaper than having a lot of paperwork, especially since it was a 3U CubeSat and it was not already full.
So given that on this vehicle you had the volume available, but in other instances volume is at a premium, are there plans to further reduce the size of this system, and how do you plan to go about doing that?
Yes, our current prototype, I don't have it here, is about a third of a U, set by having multiple Elroy units flashing simultaneously, and also because we are using components like an 18650 battery that we've flown previously, and because we did not do the engineering to shrink it down. This size is the size that we think we can get it down to for use in a CubeSat. If it's in a larger satellite or out in GEO, then it will be a bit larger, but not that much larger. Most of the volume of this is a battery sufficient to get through about a day without sunlight. And this 2 square centimeter solar panel in order to power it when the tumbling satellite does show it to the sun. If you were willing to build it into the satellite and power it off of the bus power, maybe back at the batteries, then the components you need are really quite small.
Okay, one more question. So assuming that you managed to get widespread adoption on, let's say, proliferated LEO constellations, is there any concern about number of blinking lights and potential problems that could cause for astronomical observations?
Yes, we've thought about that. It turns out that this at a distance of 1,000 kilometers, if you looked at it with any size telescope, is going to be dimmer than the natural sky background. For astronomers, it's about 23 magnitudes per arc second, per square arc second. And the only way that you can actually see it is if your telescope tracks the satellite, or if you have an instrument, a very large aperture, which also looks specifically for blinking laser lights with a very narrow bandwidth. So this produces about 4 photons per square meter per blink. And it blinks, then a millisecond later, it's 7 meters away and it blinks again. And 7 meters away is enough to not be on the same pixel if you're using standard 1 arc second type pixels.
Okay, well, thank you very much. I think we're going to move on to the next talk, but thanks for joining us and answering the questions.
Thank you.
So we are going to transition to a paper submitted by Northrop Grumman Corporation. We have Ted Nye with us. He's going to talk about advancements of a microsat for on-orbit satellite surgery. For folks who haven't seen the paper or his talk, very interesting stuff here. So we're interested to hear what you have to say, Ted.
Great, thanks, Darren. Good afternoon. Thanks for tuning in. We've thought about this kind of a problem for maybe half a dozen years, and we're very inspired by the biomedical industry, Da Vinci robot system, RoboDoc, those kind of things, where they could actually do surgery on people. And it's a little different, but it brings you down the road of not only making the machine, but you also have to make the operator's environment. And we thought that was particularly interesting to explore. What we're after is really a technician in space, something that can mate and demate parts. So it has to deal with fasteners, it has to deal with harness, it has to deal with splicing, connectors, thermal protection. We wanted to be one level more deep than just bringing up a big assembly and just attaching it together with pre-thought out assemblies. We kind of went down a road of telerobotics with artificial intelligence for assistance because the complexity. You think about assembling a satellite on the INT floor autonomously, that's really hard to do. So hard nobody even really considers something like that. Maybe there's automated robotics in some parts of the assembly, but not the whole thing. We also thought about making our machines more on the human scale, where it has the dimensions of arms and the forces of arms and the speeds of arms. And we started out with a test bed. We didn't want to launch into space with some type of a space vehicle concept because, well, to be honest, we don't quite know what we're doing yet. We're figuring this out as we go, and it's very, very complex, as we found. And much like the biomedical robots, we're spending a lot of energy right now on eye-hand coordination, which is both subjects are very difficult. The eyes, basically your cameras, seeing depth, seeing range, seeing in the lighting conditions, and then getting the hand coordination to do what you want it to do, given delays, given noise and signals and that sort of thing. So it's been pretty exciting for the last couple of years, and I hope to talk more about it as time goes on. There's a lot of information in paper, but we're moving all the time though, so the system has changed actually quite a bit since last February, but we're continuing learning. Okay, thank you.
Okay, thanks for the overview. So a couple questions here for you, Ted. So it seems, especially in seeing your talk with the stations that you had set up for controlling this, that there are certainly challenges for an operator to control this type of equipment, even in the same lab. Can you talk about thoughts about latencies if you were trying to use the system with additional delays for a vehicle in orbit, especially if you're out, further away, geo or something? You have several seconds where you have a big latency you're dealing with.
Yeah, that question is big on our minds. There's a couple things in our favor, though. One is that when you're doing things in space, deployments, separations, you want things to go really slow. And in this case, if we're trying to salvage a traumatized spacecraft, there's no need for speed, and you can take your time and do things slowly. So there is going to be lags, and we've thought about feed forward systems, things that the border or augmenting virtual reality. We haven't pursued that just yet, but seconds of lag in a lot of our signals, and it just takes a very patient operator to do those maneuvers. If it's one operator, there's just way detachment of the vehicle to the host, and the other one will actually perform the surgery. So the bad news here is getting more and more complex, but we're just seeing where this path takes us. But those are the delay. It's a big deal, and there's a lot of publications on delay and how people are dealing with it, but it'll be a necessary evil that we'll probably have to deal with. And geo altitude is the only thing we're looking at as the highest altitude, nothing to another, the moon or anything like that.
So, obviously spacecraft are very complex systems. What percentage of anticipated repairs do you think could be carried out by a system like this with the limited tools that you'd have available?
Yeah, great question. Well, when I think of the Galileo spacecraft with an antenna that got hung, or other spacecraft that we've had that have things that got hung during deployments, you just wish you had somebody that could kick it. And in fact, my experience on shuttle programs were that we did have hang-ups sometimes when we deployed in the early days, that an astronaut was able to actually make a correction and a fix. But the likelihood of getting down inside a spacecraft, getting into those avionics, yeah, that's exceptionally challenging. I don't know if we'll ever see that in our lifetimes. But so it kind of depends. And every failure that I've seen, and I've studied them for many years, they're all different. But you just wish sometimes that you just had a way to just move that catenary a little bit over to the side, or that solar wind blew your deployable over just a little bit, and you just, if there's a way you could just move it over a little bit. So a lot of times it's just inspection, but now we'd like to have the ability to touch, and it has to be, it has a lot of constraints on the problem. And that's if you're doing repair. If you're going to do assembly, it might be a different type of system.
So with some systems that might be in need of repair, if they're in a tumbling orientation, it could be very difficult to kind of match that. Any thoughts about how to address that scenario?
Yeah, so I've looked at how MIT did spheres and some of the tests that were done in the early days, trying to match tumbling rates, and I think that's a lot more of the G and C part of how the vehicle has to control itself. There's going to be limitations to that, and again, the concept we have right now is that we're attached to the host. We are a parasite on the host, if you will, and we can be deployed off that host if the need be. So if the host is already tumbling, yeah, we're going to be tumbling with it because we're in relative space, so to speak, not absolute. But and it's really, in our thought, we're not designed to go out and chase down some other spacecraft that could be spinning out of control and then figure out some way to attach to it. That's a little different problem, but we haven't pursued that direction. So we're assuming that we're going to be on the host, and we'll be traveling with the host rates, whether they be in rotation or translation.
What about safety-related concerns? You send this thing out to do some repair, and how do you know it doesn't do more harm than good?
Yeah, those are really good. So when I've flown space experiments on the shuttle, oh boy, we lived through that stuff big time on space station as well, and do no harm. So when we put auxiliary payloads, if you will, on national platforms, there's a big rule of thumb that says, no matter what you do, you have to be passively safe, and you have to nowhere come near risking the primary mission. And I take those to heart. I think that's a really good constraint to put on us. So fail safe and be behaving in a way such that we can't get out of control is going to be really important. So that has a lot to do with flight ops. It has a lot to do with how we touch and grip. Our initial attachment methods right now are very soft. We're using catheter type techniques to not only grab things, but to be able to wrap around things if we need to. And then you work your way in, kind of like a rock climber climbing a face. You know, you find your way to where you can get little holds and get locked in, and now you rigidize yourself, and now you can be able to react those forces. It's a messy design because you have to be able to turn a fastener. You have to react some substantial torques. And again, if you're in a triage where you're trying to save a multi-billion-dollar platform, you know, I think that anything goes in those points. But safety is a huge part of this, and I think the ConOps are going to take a lot more development than our straw man plans that we have now to make that happen.
Okay, Ted. Well, thank you very much. We might circle back with some additional questions. We want to make sure we get everybody in before
Sure.
running out of time. This topic could go on for quite some time. There's a lot of interesting stuff to talk about.
Thank you.
All right. So the last paper we're going to have for the discussion today is from Ryan Conversano from JPL, and it's about cathode and electromagnet qualification status and power processing unit development update for an electric propulsion system. Welcome, Ryan.
Thank you very much, and thank you everyone in attendance. I am the PI for the Astreus system that is under development at JPL. The Astreus stands for Ascendant Subkilowatt Transcelestial Electric Propulsion System. So based on the name, obviously we're shooting for beyond Earth targets, although the system could technically be used for near Earth. It's primarily designed for anywhere from Venus to Pluto. It's targeting a 10 kilogram dry mass or less, power throttling of up to about 1 kilowatt, with 50% total efficiency of the system, and at least 100 kilograms of xenon throughput. Quick status update: the thruster has been developed, designed, fabricated, and is currently in its long duration wear test prior to environmental qualification. We have a separate independent cathode life test that's ongoing. We just recently passed 6,000 hours of constant operation at the highest discharge current that the thruster needs, which exceeds the lifetime requirement of the cathode. Second cathode also performed 25,000 ignition cycles from cold start, which is the largest number of cold start ignitions on a lanthanum hexaboride cathode to date in any published literature by about a factor of 2.5. We also recently completed the required number of TVAC cycles on a set of electromagnet coils that the thruster uses, with about a 90% margin on total number of deep thermal cycles. So we're pretty comfortable there. And then the power processing unit, which is another large portion of the paper, we did a deep dive into each of the different converters required for the system. But overview, the system is about 90% or better total power conversion efficiency. And it's going to fit within a 2.5 liter packaged volume and be under about 3 kilograms. So very ambitious targets, but so far everything that we've built has fallen within those targets.
Well, thanks for the overview. A couple questions here. So for those of us who aren't as familiar with the different competing thruster technologies, do you think you could talk a little bit about how this thruster compares with other compact thruster technologies?
Sure. So I'll actually use my background. This is a picture of the MASME, the engineering model MASME, or magnetically shielded miniature Hall thruster, which is the thruster in Astreus. It is a Hall thruster with a center mounted cathode, as you can see right there, that center plume. A Hall thruster uses crossed electric and magnetic fields to confine a plasma, and then uses an electric field to electrostatically accelerate the ions preferentially to generate the thrust. Rough idea of scale, right now it looks like it's the size of my head. It's actually about the size of a coffee cup, maybe slightly larger. And it's magnetically shielded, which is novel in this scale. It was the first magnetically shielded Hall thruster that successfully operated under 1 kilowatt in the world. And to date, it looks like we have a lifetime something on the order of 400 to 500 kilograms of xenon throughput, which is on the same order of magnitude that you get with multi-kilowatt Hall thrusters. And so you're looking at a device that would last longer than the amount of propellant you could possibly carry on a SmallSat. Other technology of this scale, you have gridded ion thrusters, which obviously have grids. they tend to operate at higher ISP, but we've already demonstrated almost 2,000 seconds on this device, and the need for more than that on a SmallSat really has yet to be seen. And then there's obviously microelectric propulsion, but that's well below 100 watts, which is not really an area that we're targeting.
Okay.
Come over to this side so you can see the rest of it.
Do you have any future plans to include thrust vector control or gimbaling with this type of system?
Funny you ask, yes. So in the paper and presentation, we discussed the dry mass of the system. Right now, we're up to about 8.2 kilograms. We are actively developing a novel gimbal. There are commercial options that are kind of our backup, but right now we're looking at an internal development for a new gimbal. And that will fit nicely within the entire system and keep our mass below the total 10 kilograms for gimbal, thruster, power processing unit, and a xenon flow controller. So yes, that is something that we're actively pursuing.
And can you tell us a little bit more about the mission that this is going to go on? Where is it going, and how does it help? How does this technology help enable this application?
Sure. So right now we don't have a firm mission. We are developing this for a class of missions based on some strategic developments within JPL. The idea is to enable SmallSats to complete discovery class missions, which is deep space scientific missions, but for significantly lower cost using smaller spacecraft. And until very recently, there were no propulsion options to get you from a GTO or a GEO orbit out to Venus or out to Mars or even to Saturn, for example. You didn't have the throughput capability in a small, low power enough thruster to actually enable that to occur. And so that was really the impetus for the development of this device, which started back in 2011. Actually as part of my PhD project, and it's come a long way since then. And the main feature, as I said, is the fact that you can literally put throughput for days through this thing, and you're really throughput carrying capacity limited rather than device throughput limited. So you can go as far as the amount of propellant you can take with you.
Can you talk a little about the types of power sources that could be coupled with this? Is this primarily going to be, solar power based, or do you envision alternative powers that could be used to power this system?
Sure. So for SmallSats, we've kind of capped ourselves at around 300 kilograms or less, which is slightly larger than a standard ESPA, but fits within the ESPA Grande. Those are primarily going to be solar powered just because of the mass of an RTG, for example. But if you look at some of the previous papers that we've published, we have looked at RTG powered spacecraft that come in around 500 or 600 kilograms going to Uranus and Neptune. And those are tractable missions if you can get an RTG that'll give you 200 or 300 watts when you're out there, that you can actually complete a new frontiers style mission because this device can be used even with solar panels coupled with an RTG to throttle down as you go. The system is fully throttleable from a kilowatt down to about 150 watts. So you have a lot of flexibility in terms of how much power you develop and where you are in the solar system.
We have one question that came in about, can you use this thruster for detumbling? So let's say the vehicle was rotating around, envisioning as you're talking about the gimbaling, and maybe that plays in here. And also, how much thrust does it provide?
Sure. So I am by no means an expert on in-space tumbling dynamics, but yes, if you have a gimbal, you can provide some amount of torque on a spacecraft, and over some period of time, you should be able to stabilize, coupled with whatever ADAC system you have on the spacecraft. In terms of thrust, the peak thrust that we've measured is about somewhere between 69 and 70 millinewtons. And we can go down to below 10 millinewtons, depending on what throttle point you have.
Do you know of any programs that tend to use this technology? I know you talked a little bit about the class of missions you're trying to enable, but has there been stronger interest in any particular programs?
The most interest recently has been in the simplex mission calls. There were several electropropulsion based simplex mission calls for the prior call, and then the 2021 or 2020 and 2021 simplex missions are interested in SmallSat electric propulsion. The reality is that we have, as a country and really as the entire planet, we have very little experience with deep space electropropulsion missions. You know, the most well-known, at least in the United States, is Dawn. And then we have Psyche coming up soon, which is going to be another interplanetary electropropulsion mission, but there just aren't that many of them. And so to immediately jump into small sats going around the solar system, it's a big leap. But if we can demonstrate the device works the way that we expect it to and follow the same procedures you do with larger spacecraft, the idea of being able to go to Venus or Mars or Saturn for on the order of $250 to $300 million is a very, very appealing possibility if you can actually make it happen. And propulsion is the way you get there. So,
are there any plans to commercialize this technology outside of JPL?
Yeah, so one of our mandates is to develop commercial partnerships. We have had a prior commercial partner in a company called Apollo Fusion. They actually licensed the device and are primarily focused on near Earth spacecraft, and so they took the IP and kind of developed a more Krypton-based system, which you can find on their website. JPL, obviously, because we are looking at deep space missions where volume is a major constraint, Krypton doesn't package very well, and so we are focused on Xenon. We have some other leads on commercial partnerships that might be developed in the future that would provide us a Xenon system. But the reality is that JPL is more than capable of producing this system in-house if required. We have a long track history of developing successful technologies for flight. And so whether we do it for a mission strictly in the in-house or developing it commercially, I think either way we'll get stuff flown around the solar system.
All right, very good. Thank you, Ryan. So I think we've gotten through all the talks here, but we can circle back to any of the others. So certainly for those in attendance, if you have questions for any of the other talks, please send those in because we can do a round robin to revisit some of the other ones. But I wanted to start with circling back with Ted Nye from Northrop Grumman.
There we go. Sure.
Yeah, we're doing pretty well with video switching here. Thanks for coming back on.
Yeah.
So getting back on the topic of the surgical arms, can you tell us a little bit more about the types of feedback sensors that the system has and what some of the trades are there? How can a remote operator really have a good feel for what they're working on and make sure that they're making the right modification?
Yeah, so in telerobotics, haptic feedback is really a pretty big deal, and it's a really good enhancement. With ours, right now we're up past 45, almost actually on our way to 60 roughly right now, channels of wireless. We've got a lot of wireless going back and forth. Wi-Fi, Bluetooth, NRF radios. We've got high-speed .802.11s. Haptic feedback. Even though the robotic arms, the Cyton robot arms, they do have torque, position, velocity, and acceleration capability. There's a PID controller in each joint. So right now we're using that human in the loop to do most of our positioning. We do have telemetry that comes back from the vehicle. It tells us how much pressure we have in our propulsion system, for instance. But for the most part, right now it's really just based on roughly the visuals an operator gets from the telerobotics. So we don't actually close the loop, if you will, with a lot of feedback. Everything's kind of driven by visual.
Seem to be
All right. Did I break up?
breaking up a little bit.
Hear me all right?
We can hear you now.
Yeah. Sorry, I wasn't hearing you. There you go.
So one other question about is there interest from any particular programs about trying to use the system that you've developed, or is it still very much in the R&D phase?
I'd say it's very much an R&D phase. We've had people look at it, and they're very anxious to fly it, to try it out. But we've got a lot of kinks yet.
Maybe we should drop the
we've got a lot
video.
of
We're having some breakups
can
here.
you have something in space? Oh, can you? Yeah. Okay.
Can you try, Ted, turning off the video for a second? It seems like we're having some bandwidth challenge on your side.
Sure. Let me. Let me.
Maybe that will help
Better.
with the audio.
Better. Will that help a little bit?
It seems to. Yeah. Let's continue like that for a moment.
Sure. Let's see. Your question was. Remind me again.
About programs that may want to use this.
They may want to use
future.
it. Yeah, so we've had people look at it, and they've had an interest of, hey, let's get this up at a flight experiment. But we really do want to turn fasteners. We do want to splice and cut wire, and that takes a lot of mechanics that we're still developing on the ground. So it's not just sitting down and designing like a spacecraft. It's about, like I say, the machine in the ground as well as the vehicle. Sure enough yet, quite honestly, to going out and trying a flight experiment. But it's come up a lot, and it's a question of what utility could we show in space. So it's on the radar, but I don't think we're to a point right now we're mature enough to commit and spend the resources and the energy it takes to do something, perhaps on space station or on a free flyer.
Okay. One additional question about the perception or by international parties. Is there any concern that this technology could be viewed as hostile?
Well, that's a good question too. So I spend a lot of energy looking at international journals and what other people are doing, and it's a topic that is out there, so to speak. But our interest is truly harvesting old equipment, fixing things, and that's kind of really where we're pointed. If with any of these types of machines, you could do things, but I think we stay within 100 yards of our host, and we're really designed to be, if you will, programmed to work with our host. In fact, we need the comm system of our host. With the ConOps we have right now. So we're not a free flyer. We can't, we have very, very low delta V. We use cold gas thrusters for safety, and we don't want byproducts, hot or debris, to go into our host. So right now the ConOps and the spectrum is really just looking at a cooperative target that we work with.
Okay, thanks, Ted. We got some other questions that have come in for others, so we're going to switch gears.
Thank you.
We have a question for Ryan about the thruster system. What gimbal angle range are you targeting for the gimbal system?
Right now, our system would do plus or minus 15 degrees, so we can trace out a 15-degree cone, which would be the half angle, I guess. So it would be a full throw of 30 degrees from one limit to the other. Okay,
very good, thanks. And then another question for Calvin regarding the compact lightweight solar array. Can you talk a little bit about the technology insertion plan for how this will be adopted on future missions?
So we'd like to do more testing from end to end, including getting the solar cells placed on and running the interaction between that and the substrate, and then we can insert it into any program that requires a long wingspan like that, and then we can. It is pretty much a customized solution. It's not like it will bolt on directly, but it has to be worked out. So
or do you have any plans for commercialization of this technology?
not at the moment, but yeah, not at the moment.
Okay, very good. We're going to cycle around to David Palmer from Los Alamos.
Hello?
Oh, very good. Welcome back, David. Question for you on the Elroy system. So, given the challenges with the NMTSAT, what's the next plan for flight demonstration of this system?
Okay, we currently have a couple of Elroy satellites on a pair, a couple of Elroy units on a pair of satellites that will be launching in April 2021 if everything goes well, and another satellite near the end of 2021.
And are those of a similar design with the diffusers and so on?
Yes, these are what we call the universal prototype, which is about 1/3 U unit with 4 laser diodes, so we can run multiple experiments at one time.
Can you talk a little bit about the ground architecture if this were to get a wide scale adoption? How do you envision different ground telescopes tracking? Is it something that can be taken on by existing assets, or would this require deployment of additional telescopes to stand up a ground network to monitor these?
Okay, it would probably require additional telescopes, but these are telescopes of this size, so you could probably do the optics and mount for about $30,000 to $40,000. You can, and of course there's facilities cost, because just sticking a telescope somewhere, putting it in a shed is a comparable amount of money. And that would probably be best co-located with an existing facility, such as Exoanalytics has a lot of telescope farms. The ground station has to be at night during the observation, which is a disadvantage over radio. And it's easier if the satellite is in sunlight as opposed to eclipsed, because then you can use the telescope and a video camera, CCD, to locate it, lock in the tracking, and put the light from that on a single pixel detector, which is cheap and can be very high efficiency. If you do not have the sunlight to detect satellite, then you need an imaging photon counting detector, and then you just need to have satellite within the field of view. But imaging photon counting detectors are currently more expensive than the telescope itself. However, there's a lot of work in this field for making solid state imaging photo detectors for the LiDAR market for self-driving cars and other applications. So we expect that to progress rapidly.
Have you explored any partnerships with the organizations that are currently involved in tracking of space assets? You know, as a kind of an adoption plan for if this goes smoothly, what comes next?
We have not done any formal talks. We've discussed it when we meet up at places like SmallSat. And so if anybody has ground stations that wants to get in on this business, they can call me.
Okay. Also, any plans or thoughts about commercialization of the spacecraft side of this system?
Yes, we have a commercial call which recently closed. So we asked for companies who might be interested in making this object, and we cannot announce any results of that yet because we are still evaluating them, but we did get some interest.
Okay, very good. We got one more question for Chris Wilson for NASA Goddard. Chris, can you talk about the relevance for this processing system that you have for some of the Goddard servicing missions that are planned?
Yeah, sure. So the one great thing about having better onboard capabilities is you're able to do a lot more applications. So we actually present. So if you guys check it out, we actually present with those groups a lot of the times. But a lot of this technology is to enable some of those more computationally intensive algorithms. We're currently, so I don't think I'm not sure if which I can talk about, but we are in discussions, working with the on-orbit assembly groups and stuff.
Okay. There's going to be, we're going to do a transition back to Aaron Rodgers. A final wrap-up question.
Yeah, so I'm chairing a session tomorrow with the Space Access, and I wanted to ask a kind of a quick lightning poll of everyone here. If you had an opportunity for a non-traditional way to get to orbit, what would you choose? Orbit or beyond. So previous answers included space elevators, slingshots, back of a superhero. Anything you'd like to offer to this mix?
Deep sea cannon, direct to orbit insertion.
Nice. Okay. Calvin, David, Ted, Chris?
I've always liked rotating tethers.
Okay. Anyone else?
We've looked at electromagnetic guns, and it takes one heck of a gun to shoot a CubeSat to space. But yeah, I don't know if we're going to see that in our lifetime either. Shoot that thing, yeah.
Pretty much anything but water, I think, is going to be pulverized. But
yeah.
hey, water to the space station.
Yeah.
Great, Calvin. Anyone on your side? What's your preference?
Maybe a catapult.
Okay. Great. Did I hear anyone else? I didn't hear from Chris. Did you have a?
Well, I think a lot of the great ideas have been taken, but I would say just an Amazon Prime dash button for any of those would work great for me.
Great. How about you, Darren?
I saw one comment came in for a very strong spring, which I thought was a good one. Would have to be a big spring.
Oh, trampoline, good too. Hey, well, thank you, everyone. I appreciate your help. Thank you to Darren for moderating the panel discussion. Enjoy the rest of the week and the webinars to follow. And again, thank you to all our speakers and your participation in this session. Good night, everyone.